So in the previous video, I've been talking about something but never really explaining it, and that is thrust. So one might ask, what is thrust? Well, to answer that, we have to ask ourselves, how do rockets work? Well, rockets are based on a simple law, which is Newton's third law of motion, which states that for every action there is an equal and opposite reaction. How does that apply to rockets? Well, as I said in the previous video, and if we consider a chemical rocket here, so we're gonna focus on chemical rockets and specifically on liquid fuel rocket engines. So, as we said in the previous videos, fuel and oxidizer are considered propellants. So, these propellants will mix together inside the combustion chamber in here, and as you see in here too. So, they will mix together and then they get ignited, so they will burn, and therefore after they burn, they will get heated up. After heating them up, now they will vaporize and we've got hot gases now inside that combustion chamber, and due to that hot gases and due to that great amount of heat that was transferred, due to the great amount of heat and the great temperature there, the really high temperature there, now we've got a high pressure. And so these hot gases, those hot gases inside the combustion chamber will try to get out through that nozzle, because the pressure or the ambient pressure, the atmospheric pressure surrounding that rocket is less than the pressure inside that combustion chamber. So the gases will try to get out. And now we're talking about exhaust gases. Now, once those exhaust gases leave the rocket or leave the nozzle, we're talking about an action here. So that is the action. The action is the gases being or getting out of that nozzle. So as they try to come out of that nozzle as an action, we will get a reaction, which is of course the lift up of the rocket. And this is basically how rockets work. Now, when we talk about rocket science, there are four fundamental parameters, and there are thrust, mass flow rate, specific impulse, and weight flow rate. We're gonna start off first with thrust. So, what we should say, what is thrust? So, the good question is, what is thrust? So, thrust is the force produced by a rocket propulsion system acting upon a vehicle. In a simplified way, it is the reaction experienced by its structure due to the ejection of matter at high velocity. It represents the same phenomenon that pushes a garden hose backwards or makes a gun recoil. It is a reaction and action thing, or it is of course based on Newton's third law of motion. So if thrust is a force, and we know that force is of course, according to Newton's second law of motion, is equal to ma, the mass, times the acceleration, or in other words, it is the change in the momentum over time, or the time derivative of the momentum. And we know that momentum is of course the product of the mass times the velocity, and therefore we're talking about the time derivative of the product mv, so the mass times the velocity. Now, in rockets, the mass of the propellant is changing, but the velocity, VE, the exhaust velocity at which the gases are exiting the nozzle, is constant. And we will see why is that. We will see why it's constant, why it's not disturbed. So the velocity is constant and we've got a changing mass, and therefore the thrust F becomes the time derivative of the mass times the exhaust velocity of the gases, and the mass is of course the mass of the propellants, because the propellants are now turned into a gas. And that would be m dot. M dot means the time derivative of that thing. So in here, m dot means the time derivative of the mass. So whenever you see a dot, it means the time derivative of that quantity. So m dot times VE, the exhaust velocity of the gases. But since we said that thrust is the reaction experienced by the structure, there is one thing that we did not take into account, and that is the atmospheric pressure. So what about the effects of atmospheric pressure? What about the force caused by the pressure of the atmosphere? And so in our thrust equation, we did not take into account the force caused by the atmospheric pressure. In other words, that equation is incomplete. So to see the whole or the complete thrust equation, we have to consider the forces on the gases. The force on the gas. And so to see that, let's take a look at this. So to see the force on the gas inside that combustion chamber and the nozzle, we will consider this closed nozzle. And so we know that the force is of course equal to the pressure times the area. But in this case, the area is changing. As you can see, we've got different shapes, and therefore we need to integrate over the complete surface area of the combustion chamber and the nozzle. And therefore, the force on the gas inside the combustion chamber and the nozzle is of course the surface integral, or also known as the contour integral of the pressure times or multiplied by the area element dA. So the pressure multiplied by the area element integrated over the whole or the complete surface area of the combustion chamber and the nozzle. Now we have to remember that in the real case, the nozzle is not closed, it is open. So we have to evaluate the forces on the gas when the nozzle is open. And we know that the pressure, or it's logical to think that the pressure in this side is always greater than the pressure on this side. So the pressure, of course, on the inside of the nozzle and the combustion chamber is greater than the pressure on the outside side of that nozzle. And so if we consider this infinitesimally thin element, and this is known as the control volume approach. So we've got through that element, we've got a pressure drop. And so on this side of the element, we've got a pressure, or we've got a force that is equal to the pressure minus the change in the pressure, or the pressure drop, times the area of the nozzle. And so as we go further to the right side of that nozzle, or as we go out of that nozzle, we can evaluate the pressure on the exit plane of that nozzle, which is of course PE. Now be careful, this is not the ambient pressure. This is the pressure just before the gases exits the nozzle. It is the pressure at exactly the exit plane of the nozzle, which is of course equal to PE. So we evaluate it to be equal to PE, and therefore the force would be equal to PE times AE, and of course AE is the area at the exit plane of the nozzle. And therefore now we've got a retarding force which is equal in magnitude to PE, the pressure at the exit plane of the nozzle just before the gases exit the nozzle, times the area of the exit plane of the nozzle. And now we've got the equation for the forces on the gas, which can also be written in the form of m dot times VE. So the change in the propellant mass times the exhaust velocity of the gas. And now we said that the flow of the gas is not disturbed. There is no turbulence. And that's because the exhaust stream at the exit plane of the nozzle is not affected by the ambient pressure, since the gas is traveling at supersonic speed, and hydrostatic effects can only travel at the speed of sound. So what does this mean? It means that the hydrostatic effects, which is the effects caused by the ambient pressure, would only travel at the speed of sound. And in here, the hot gases coming out of the nozzle are traveling at supersonic speed, more than the speed of sound. And therefore, the hydrostatic effects would disappear. and therefore we would get a constant flow of the gas. So the flow of the gas would not be disturbed, and therefore the exhaust velocity is constant. Now let's take a look at the forces on the rocket itself, but not the gas. We're talking about the forces on the rocket. So again, we can evaluate the forces on the rocket by integrating, so by multiplying the pressure times the area element integrated over the whole surface, or the complete surface area of the combustion chamber and the nozzle. And again, we're not talking about a closed nozzle here. The nozzle in the real case is always open. So to evaluate the forces on the rocket, we will consider the unfiring motor. So this is static, this is not moving. This engine here, or this motor, it is not moving, it is static, it is unfiring, it is cold. So since it's static, it means if we draw a plane through that nozzle, through that combustion chamber and nozzle, it means that the forces on one side will balance the forces on the other side of that plane. Just like if we draw the plane in here, or if we draw them in here. Now this is interesting. Now this means that the forces on this side, so the forces on this side will balance the forces on this side, which is of course, and that force would be of course the product of the ambient pressure times the area at the exit plane of the nozzle. So since we're talking about the surrounding air in here, so that force would be equal to the ambient pressure times the exit plane area. So now what we concluded is that the forces on this side are equal to the forces on the other side of the plane. So PAAE is equal to these forces, or these forces due to the atmospheric pressure. And this is for an unfiring motor, but in real case we've got a firing motor. The motor is of course running. And so as the gas exits the nozzle, we will get no hydrostatic effects since they travel at supersonic speed, since the gas travels at supersonic speed, and therefore we will get no atmospheric, or we will get no effect due to the atmospheric pressure at the exit plane of the nozzle. And so we will have a retarding force of magnitude of PA, the ambient pressure, times the exit plane area, because these forces are still present when the motor is firing, when the engine is running. And so these forces, which we concluded that are equal to this magnitude, or this quantity, of course, the ambient pressure times the exit plane area. And so again, these forces are still present, and these forces, or that force, will be a retarding force, and therefore it's negative PAAE. So these are the forces, or these are the forces on the rocket itself. Now we can take those two equations. We've got the equation for the forces on the rocket and the equation for the forces on the gas. So we can take those two equations and we can conclude from the first equation, from the forces on the gas equation, that the integral of, or the contour integral of the pressure times the area element would be equal to m dot VE, the m dot of course being the mass flow rate times the exhaust velocity of the gas, plus, so we change this product here to the other side of the equation, so we've got plus PEAE, the pressure at the exit plane of the nozzle just before the gas exits the nozzle, times the area of the exit plane of the nozzle. And therefore, if we take this in here, so taking that in here, that means that the forces on the rocket thus becomes m dot VE plus PEAE minus PAAE, and PA is of course the ambient pressure, and AE is again the area at the exit plane of the nozzle. And that is of course the thrust equation, since we're talking about the forces on the rocket. So that is the thrust equation, that is the force of the thrust force. So that is the thrust equation, which is of course equal to m dot VE, the mass flow rate, times the exit, times the exhaust velocity of the gases, plus the pressure change from the pressure inside the nozzle just before the gas exits the nozzle, minus the pressure or the ambient pressure times the area at the exit plane of the nozzle. Now if I want to write it down in a simpler way, maybe I want to write it down as m dot times a velocity, and that velocity is the true velocity, or is the effective exhaust velocity, and that is known as the rocket thrust equation, with of course the m dot being the mass flow rate in kilograms per second, VE is the exhaust velocity of the gas or in meters per second, and the area or AE is the exit area of the nozzle in meters squared. Of course, PE is the pressure at the exit plane of the nozzle just before the gas exits the nozzle or measured in newtons per meter squared, and PA is the pressure outside the nozzle, or in other words, it is the ambient pressure. C is the effective exhaust velocity. It is the true exhaust velocity, which is of course measured in meters per second, and C is of course equal to VE plus PE minus PA times AE over m dot. So what we do here is divide this side of the equation by m dot, and therefore we'll get the C, or the effective exhaust velocity, or the true exhaust velocity.